In this lesson, we're going to start by relating exponentials to logarithms. First, we're going to explore how exponentials and logarithms are kind of like undo buttons to each other. And then because of this, if we started off with a graph of an exponential function, which I've already explained in a previous lesson, then we can use it to actually graph an exponential function, which is going to look something like this. After we learn how to graph simple logarithms, like this one, we're going to pay particular attention to a part of the graph, and then we're going to map it under some transformation to a new point. So by the end of this lesson, if you can understand how I actually do this mapping from here to here, you will know how to graph basically any logarithm I throw at you, and that's a really useful skill to know. So that means this is going to be a lesson on graphing logarithms. So before we actually talk about graphing logarithms, we need to remember that logarithms and exponentials have a very careful relationship to each other. So I want you to imagine that you started off with some number, which we can call x, and then you put it into an exponential function, which we can call a to the power of x. What you get out is this new number, which we're going to call y. So to give you a really simple example of this, I want you to imagine that capital Y is the same thing as 2 to the power of little x. So this over here is the function of x. Well, if you imagine that capital X was equal to some number, like let's say it was equal to 3, then this would just be 2 to the power of 3, which of course is just going to be 8. Now, if you've been watching my videos on logarithms, you'll know by now that logarithms undo the action of exponentials. So we can draw a logarithm like this. So the idea here is that if you started with the number x, put it through a to the power of x, you get some number y. Now if you put this through this function again, you're going to get back to the exact same number x that you started with right at the beginning. So if we use the same example, where a is equal to 2, then we can see that y goes into log, so you get the log base 2 of y, and the result is just x. So if we put the number 8 back into the log base 2, then we'll end up with the number 3, which is what we started with right at the beginning. This is easy to see because the log base 2 of the number 8 can be found by dividing 8 by 2 as many times as we can. If you do it once, you get 4. If you do it twice, you get 2. If you do it again, you get 1. And that took 1, 2, 3 divisions. So the log base 2 of 8 is just the number 3, as we found. So because logarithms have such a close relationship to exponentials, then it makes sense to look at the graph of exponentials to figure out how to graph a logarithm. To draw exponentials quickly, remember that we need to think about two particular points. Now a to the power of 0 is always going to be equal to the number 1. So when x is equal to 0, then we always get 1. The next point we care about occurs when capital X equals 1. A to the power of 1 is just going to be a, so depending on what your value of a is, a just shows up somewhere else. Now, as we discussed in the lesson, where I showed you how to actually graph exponentials, we then just connect these 2 points with a graph that looks like this. So I'm not going to say too much more about how to actually graph these exponentials, because I talked about that a lot in a previous lesson. So you can watch that lesson if you'd like to figure out more. But to find the graph of a logarithm like this one, we are going to need to reference this graph of this exponential pretty heavily. So I've gone ahead and actually copied over this graph, and I've drawn on this special line, which is y equals x. You'll see why it's special in just a minute. Now I want you to understand something really important about the way logarithms and exponentials interact with each other. Notice that for an exponential, when we put in the number 3, we got out the number 8. But then for logarithms, the opposite happens. It is the inverse function, as we said. So if you put in the number 8, you're going to get the opposite thing back. You're going to get the number 3. So if you look carefully, I want you to notice that the logarithm seems to actually swap the outputs and the inputs when compared to the exponential. So for the exponential, 3 goes in and 8 comes out, but for the logarithm, 8 goes in and 3 goes out. So they've been swapped. And since x is usually thought of as the input axis, whereas y is thought of as the output axis, well, the logarithm seems to just be swapping x and y. You can see that y goes in and x comes out. This also makes a lot more sense when you actually look at these 2 special points over here. It turns out that these 2 special points are also the only points you need to actually graph a logarithm. So for an exponential, if you put in 0, then a to the power of 0 is always going to be 1. And logarithms should do the opposite. the log base a of 1 should always be 0, and that is of course true. This is also something that's really useful to see up here. If we put 0 into an exponential, we're going to get 1, because a to the power of 0 is 1, as I've said. And then if you put 1 into a logarithm, the log base a of the number 1 always equals 0. And you can basically just see the coordinates here. Notice that you've got 0, 1, which is what we have here. And then over here we have 1, and then we have 0, which is what we have over here. So then we'll just do the same for the other point. If we put in the number 1 here, we'll get a. And then the log base a of a is just going to be the number 1. And so this just leads us to the exact same conclusion. Notice that over here we have 1a, and here we have a1. So we've again just swapped x and y to get the new point. So remember, this is true because the log base a of a is always going to equal 1. So if x is equal to a, then y is going to be equal to the number 1. And I think that's just about all we needed all of these markings for. So let's get rid of all of them and continue talking about this actual graph. So now we're finally ready to talk about why I actually drew this line onto the graph. If I actually copy these points right over to the other side, I want you to notice that the new points are just reflections of the old points along this line. It's almost as though this line over here is a mirror and these points are being reflected. But if these 2 points are going to be reflected, then shouldn't every point on the logarithmic graph also be reflected? Well, if that's the case, then all of these points are going to reflect over, and you're going to end up with a graph that's going to look something like this, as you can see. So if this graph over here is the graph of y equals a to the power of x, then this graph over here is actually the graph of y equals the log base a of x. Now, if these two graphs are actually reflections of each other, there is one important side effect that I need to tell you about. Notice that exponentials never have any negative y values. And because we're swapping x and y, then that means that logarithms never have any negative x values. And this is something you should try in your calculator. If you tried typing the log base a of any negative number, you are going to end up with a maths error. So I've just randomly picked to type in the log base 10 of negative 4, and as you can see, the calculator has no idea what the answer is. And that's because the log base 10 of negative 4 is just not a real number. Now before I show you how to transform this graph and draw it any way you like, let's just rehash everything we've said so far. We said that exponentials and logarithms are inverse functions of each other. And for any two inverse functions, there are always going to be reflections along the line y equals x, because you've swapped the capital X and the capital Y axis. So now, if we'd like to actually transform this graph to a new graph, I'm going to use the standard technique that I've used quite a few times by now. I want you to imagine that we're going to track around a particular box somewhere on the graph. So I want you to imagine that this capital X and capital Y axis represent our original log base a of x, and this little thing over here is kind of like a photograph of a little piece of it. Under the action of a transformation, I want you to imagine that this little window over here ends up moving to some new place on our new axis. But then, whenever this window actually moves around, I want you to notice that it actually drags the function along with it. And if that's the case, then all you really need to do is to just track a few points from the original graph onto the new graph. And I'm going to track this point and this point over here. And this point's going to end up here, whereas this point ends up over here. Now, one of the cool things about a simple transformation like this is that as long as you know where two different points go, then you technically know where the whole graph goes. So the asymptote, which used to be here, ends up over here, and this point over here ends up right here. So then the only question is, how do we actually go ahead and map these 2 points to this point and this point? So first we have the point 0, 0, and we have the point A1, and we have to figure out the coordinates on the new axis. So this is the most general logarithm that I could get you to graph. We have y equals k log a, b times x minus c, all plus h. So in order to actually graph this general transformed logarithm, we're going to need to follow a few steps. The first thing I'm going to do is I'm going to rearrange this so that it looks a little bit like this. So I'm going to start by moving the h to the other side, and then dividing by k. So once you've rewritten this in this format over here, then I want you to notice that this y minus h on k is kind of like this capital Y, and this b times x minus c is kind of like this capital X. So once we've rewritten this, we can see that capital Y equals y minus h on k, and capital X equals b times x minus c. So now at this stage, we have a cool relationship between the capital X and capital Y axis and the little x and little y axis. But the only problem is that capital X and capital Y are currently the subject, and we don't want to make them the subject. We want to graph little x and little y. So let's make little x and little y the subject of both of these equations. So we can start with this equation up here. To make little x the subject, we just divide by b and then we add c. And then while we're at it, we might as well put little x on the left-hand side. So then we notice that little x is going to equal capital X on b plus c. After this, we want to do the same thing for y. So I'm going to make little y the subject. I'm going to start by multiplying across the k, and then I'm going to add h to both sides. And just like last time, we also want little y on the left, so let me do that too. So here we notice that little y is equal to k times capital Y plus h. So this is the general technique that you're going to follow. You're going to start with your transformed function, you're going to rewrite it, and then you're going to solve for little x and little y. Once you have these two equations, it's really easy to map all the points from the left right over to the right. So to avoid this being too abstract, let's go ahead and actually work through an example together to see how we can use this. So suppose I wanted to graph y equals 6 minus 4 times log 3 of x plus 2. To do that, the first step is to rewrite it in this form, where capital Y equals log of a of capital X. So that means I need to get this log of 3 on its own. So to do this, I'm going to need to subtract 6 from both sides, and then I'm going to need to divide by minus 4. So now I can immediately infer that y minus 6 all on minus 4 is the same thing as capital Y, and then x plus 2 is the same thing as capital X. So now that we know how little x is related to capital X and little y is related to capital Y, we just need to make little x and little y the subject, so we should solve for little x and little y. Now solving for little x is really easy. I just have to subtract 2 from both sides, so this 2 moves over and becomes negative. So this just tells us that if you know a point on the capital X axis, you just subtract 2 from it and you'll find the little x point. Now we do the same thing for y. So first I'm going to multiply both sides by this minus 4, and then I'm going to add 6 to both sides. So now comes the easy part. Because we have these two equations, drawing this transformed graph is going to be quite simple as long as we know how to draw y equals the log base 3 of x. As you can see, this is the graph of capital Y equals the log base 3 of capital X. It goes through the point 1, 0 because the log base 3 of 1 equals 0, and it goes through the point 3, 1 because the log base 3 of 3 is equal to 1. So these coordinates correspond to capital X equals 1 and capital Y equals 0, and capital X equals 3 and capital Y equals 1. In a sense, the axis is moving around to some new place, and these equations tell us how to find little x and little y from capital X and capital Y. So I'll go ahead and draw this box, and I just want to figure out where it moves to under the transformation. So this point 0, 0 over here is very easy to transform, because when capital X equals 0, little x is just minus 2, and when capital Y equals 0, little y is just 6. So it moves to the point minus 2, 6. So now that we know where 0, 0 maps to, we just want to look at this point 3, 1. When capital X equals 3, we have 3 minus 2, which is just going to make little x equal to 1. Then, if we let this be 1, capital Y is 1, so 6 minus 4 is just going to end up equaling 2. Now, just by looking at these 2 points, notice that this graph points up, but this graph points down. so that indicates we've actually flipped the graph in this direction. Now the asymptote is still going to be where the ping point is, so it's still going to be over here. But instead of the graph going up, it's going to go down instead. And now, just like that, we have a graph of y equals 6 minus 4 log 3 of x plus 2. Now, of course, you could put a little more effort into this. Like, you could actually find out where this point went. Or you could find the y-intercept by actually letting x equal 0. Or you could even find the x-intercept by letting y equal 0. But I'm not going to do any of that because I think the hardest part is finding this transformation. Once you've done that, drawing a graph like this is reasonably straightforward, and you can mark up as many points as you want to make the graph more accurate. So if that's the case, we can repeat the same thing over here. Notice that when capital X equals 0, little x is just going to be the same thing as c. So that means the x-coordinate here is c. When capital Y is equal to 0, then little y is just going to be h. So this point over here is the point c, h. Now most of the original graph is hidden here, but when capital X is equal to the letter a, then we just have little x is equal to a on b plus c. And then, when little y equals 1, we just have k plus h. Now there's absolutely no point in memorizing these two coordinates. It's much smarter for you to learn how to actually perform this transformation and to draw the graph in this way. But that just about completes my example, so let's go ahead and summarize the lesson. This was a lesson about graphing logarithms. We started the lesson by explaining that exponentials and logarithms are inverse functions. So therefore, if you started with some x and put it through an exponential, you'd get y. And then if you put it through the corresponding logarithm, you'd be back with the same x that you started with. This relationship is really important for the graphs of logarithms and exponentials. If you know how to graph an exponential, then since you're swapping x and y, you also end up just swapping x and y on the xy axis. Now, swapping x and y just corresponds to reflecting the original graph along y equals x. So if you just reflected all of these points, you'd end up with a graph that's a reflected version of the original. So in a sense, the graph of a logarithm is just a reflected version of the graph of an exponential. Now because of this swapping behavior, because exponentials never have any negative y values, then logarithms are never going to have any negative x values. Once we were comfortable with the graph of a logarithm, we then figured out how to actually transform them to make new logarithms. We said that the first step was to rewrite things so that it looked like it did over here. Once we figured out the relationship between the capital x-axis and the little x-axis, as well as the capital y-axis and the little y-axis, then we just wanted to actually make little x and little y the subject. After we make little x and little y the subject, it's very easy to just go ahead and map the points from the original capital X, capital Y axis to the little x, little y axis. Now this technique is a really powerful technique because it can be used to graph logarithms in general. I know that you could use graphing packages to just make graphs like this reasonably quickly, but it's also quite handy to be able to do this yourself, because by doing so, you learn quite a bit about how logarithms actually work. But at this point, I think you know more or less everything you need to know about graphing transformed logarithms. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.